Okay. So all I've done up to now is I've just constructed charts for the unit tangent bundle, right? So this is a chart of T1n on U tilde. Is this okay? So this this will map into a subset of this V cross W. It won't be onto V cross W. It will map into a subset of V cross W. So is it clear how I've constructed charts on the unit tangent bundle? Yes?
Yes.
Okay. I mean, what I'm doing is I have U tilde inside T1n. Then I'm applying X comma Y. That maps into V cross Sn minus 1 inside of Rn cross Rn. And then I'm composing with identity comma Z tilde. Z tilde is a chart on Sn minus 1 near this point N of Sn minus 1. So this will map to V cross W in Rn cross Rn minus 1. Okay. Is this all right? Yes?
Yes, sir. Yes.
Okay. Now what is the, so I took a function f which was in CC U tilde, right? So f was in CC U tilde. So what is the integral of f with respect to volume measure of T1m, right, over U tilde. So this will be the integral over the image, so over V cross W, right, of, let me call phi equal to psi equal to phi inverse, okay? So this will be the integral over V cross W of, let me call it capital psi. So let me just write it directly. So, so it will be like we did for the Riemannian volume of N. So this will be f of capital psi of xz right, dvol T1m of, so the basis with respect to these coordinates x1 to xn, z1 to zn minus 1 will be del del x1 up to del del xn del del z1 up to del del zn minus 1, right? Okay, so this at the point capital psi of xz, dz1 dzn minus 1 dx1 dxn, right? Is this okay?
Yes, sir. Yes, this is yeah.
Now where capital psi equal to capital phi inverse. Okay. So this is going to be the determinant, this d-vol of this basis is going to be the determinant of the change of basis, which sends an orthonormal basis of the tangent space of T1n to this basis, right? Now we can choose any orthonormal basis we want, right? So we choose an orthonormal basis of, so if I take a point, theta equal to psi of x z, so this is equal to say PV. Okay, so then I choose my orthonormal basis as follows. So mod V is 1 here. So I take as an orthonormal basis, I use the decomposition that I had here, that the tangent space to T theta T1m was R G theta orthogonal direct sum H tilde theta orthogonal direct sum V tilde theta, right? So I just take G theta, this is a unit vector, together with an orthonormal basis of H tilde theta, together with an orthonormal basis of V tilde theta, right? Okay. Yes. So for H tilde theta, how do I get an orthonormal basis? I just take an orthonormal basis of V perp, right? I take W1 to Wn minus 1, which is an orthonormal basis of V perp. And then I look at the vectors W10 up to Wn minus 1 comma 0, right? And then I take J of those, and that will give me an orthonormal basis of V tilde, right? Okay. So I take G theta, which is V0. And then I take W1 to Wn minus 1, which is an orthonormal basis of V perp in TPM. Okay. And I put xi I equal to Wi comma 0. And I put eta I equal to J of xi I, which is 0 Wi. Okay. I goes from 1 to N minus 1. Right? Okay. So then I have to look at this linear map. So dvol T1m of del x1 del xn del z1 del zn minus 1. This is equal to the determinant of a linear map T, where T goes from T theta T1m to itself. So let me write this as R G theta. So the horizontal part, direct sum H tilde theta. Direct sum the vertical part, V tilde theta, to itself. Okay, to T theta T1m. So what does this do? It maps G theta to, let's say, del del x1, then xi I, it maps to del del xi plus 1. I goes from 1 to n minus 1. And then eta I, it maps to del del zi. I goes from 1 to n minus 1. Right? This is the change of basis from orthonormal basis to this basis. Yes?
Yes.
So what is this in, if I write it in block matrix form, then what will the matrix be in a block form? Well, this the horizontal part is this G theta together with H tilde theta, right? So these horizontal vectors, these are going to some vectors, okay? But then the last part, these eta i's, these vertical vectors are going to these del del zi's. The del del zi's are vertical vectors, right? These del del zi's, these belong to V tilde theta. Because when I vary the z's, right, then my x coordinate doesn't change, the foot doesn't change, right? Is it clear? So you know, I mean, t of so what will it be? T of if I write it in block form, then it should be block upper triangular, right? Because there's no horizontal component in the for this last part, right? I mean, this is going to act on something horizontal and something vertical, right? Yes. So is this correct? Yes. Yes. Any questions? So T acts on horizontal and vertical, right? So this goes to horizontal and vertical. So if you are purely vertical, then the image should also be vertical, right? So so this acting on 0 V, what will this be? This will be A horizontal plus B vertical. Sorry, it should be the other way around. It should be, sorry, A, I think this is correct. A, 0, CD. I think it should be
Then the
lower.
vertical. So the previous one was okay. I think. This one gives me the vertical component is dependent on horizontal as well as vertical, right?
Wait. Let's see. Suppose
A
I
times
take
horizontal. This
one
is
second,
A
one
times
second.
horizontal.
Well, let me just check this. Okay, I'll just do the computation. So this acting on an H and V, right? What will this be? This will be
AH,
AH,
CH plus DV.
CH plus DV. So here what happens is the verticals are going to verticals, right? So when H is 0, then I should have just a vertical thing, right? So this is correct. If H is 0, then this is 0 comma DV. If H is 0. So I think this is correct, right?
Okay.
Yes, is this, does everyone agree?
Yes, sir.
Yes, Utshab, is this okay?
Yes, sir.
Okay, so the point is it's block upper triangle, a block triangular. So the determinant is going to be the product of determinant A with determinant D, right? Yes. So determinant T is determinant A times determinant D, where what is A? So this is the determinant. A will be, I can identify it with the matrix which sends V maps to del x1, W1 maps to del x2, and W n minus 1 maps to del x n minus xn, right? This is A, yes?
Yes, sir.
And into determinant of the other block. So the other block will be what? It will be these verticals eta I mapping to these verticals, del zi. So this will be W. So this will be right. So okay. So 0 W1 or 0 Wi mapping to del zi. I goes from 1 to n minus 1. Okay. Now the first thing is what? It's V up to W1 to Wn minus 1. This is an orthonormal basis of the tangent space TPM, right? So the first thing is nothing but d vol m applied to del x1 up to del xn, right? Yes? Right?
Yes, sir.
Okay. And what is the second determinant? Now notice that this 0 W1 to this 0 Wi this is an orthonormal basis of the tangent space at theta to TP1m. Right? Because these are perpendicular to V. So here you have the unit tangent sphere. Here you have V, and these vectors are my orthonormal basis. These are my WIs. Right? So this 0 WIs, these are an orthonormal basis of T theta TP1m, right? Yes?
Yes, sir. Yes.
Right? So this will be, and the del del ZIs are also a basis of T theta TP1m. So this will be d vol TP1m of del del Z1 to del del Zn minus 1. Right? So the point is the volume measure of the volume form acting on a basis, it splits as the product of volume forms, right? That is the point. Okay. Yes. So
Yes,
volume
sir.
form of M, and
Yes.
together with volume form of the fiber. This is volume form of the fiber. Right, the fiber is a Riemannian manifold with the induced Sasaki metric, which is isometric to the unit sphere Sn minus 1, right? And we're taking an orthonormal basis 0W1 up to 0Wn minus 1 of that and mapping it to a basis del del Zi, right? So, so therefore, thus the integral of f d vol T1m over u tilde is the same as, so now let me write it as an iterated integral over v of integral over w of f of psi of x z so psi of xz, I can write it in the form P of x and v of x z. Okay, and then what do I get? I get d vol TP1m del del z1 to del del Zn minus 1 dz1 to dzn minus 1. And then I take the other d vol m del del x1 to del del xn outside. Outside I get d vol m del del x1 to del del xn, because this doesn't depend on the zi's, right? This is a function only of x1 to xn, dx1 dxn. So I can take it outside the first integral. Is this all right? Okay. Yes.
Yes.
Yes, sir.
So now what happens? So this becomes therefore an integral over u, and the inner integral becomes this becomes an integral over TP1M of f of PV dvol TP1M of V, and the outside integral becomes dvol M of P. Is this clear? Yes?
Yes, sir.
Okay, so this is what we wanted, right? I'm integrating over the base. U is a subset of N. And then for each point in U, I integrate over the fiber, which is TP1M, with respect to the Riemannian volume of the fiber. All right? Is this clear?
Yes.
Okay, so this was for a function supported in a small open set in T1M. So by a partition of unity argument, it's easy to see that we have for any function by partition of unity. Have so let's call d lambda p equal to the Riemannian volume of TP1M. Okay, so this is a measure on the unit tangent sphere, the volume measure of the unit tangent sphere. Is this all right? Yes?
Yes, sir.
Yes, sir.
Okay. So we have that and letting d lambda equal to Liouville measure. Which is dvol T1M, that for all f in CCM, so M may be non-compact, so then I just take functions with compact support so that the integral converges. So sorry, for all f in CCT1M, the integral of f d lambda over T1M is equal to the integral over M of the integral over T1 PM f of PV d lambda P of V d vol M of P. Is this clear? Okay. And for all U open subset in T1M, the lambda of U, the Liouville measure of U, I can get as an integral over N of the lambda P of U intersect TP1M d vol M of P. Is this clear?
Yes.
The second one I get by approximating the indicator function of u by compactly supported functions, right?
Yes.
Okay, so I get this. Okay, so what is the measure of a subset? How do you get the measure with respect to the Liouville measure? What you do is, I mean, suppose this is your unit tangent bundle. So here you have, suppose in dimension 2, you have unit tangent circles, and I have some subset, right? This is my U. So what I do is I integrate over the base. The base is n. And so I integrate over the base for each point P in the base. I look at the intersection of U with the unit tangent sphere. This is U intersect TP1M. I take the Riemannian volume of this in this unit sphere, and then I integrate that as a function of P with respect to volume in M, volume in the base. Is it clear?
Can you please repeat the explanation?
Yeah, so this integral means what? I take each point P in the base, I look at the intersection of my subset U with this unit tangent sphere. That's this part here, right? This is U intersect TP1M. This black part, yes?
Right.
I
Yes,
take
sir.
the Riemannian volume measure of that with respect to Riemannian volume of the sphere, right? That is this
Yes.
lambda P of this U intersect P1M. And then I integrate that with respect to, that gives me a function of P. For each point P, I get this measure, which is changing, this volume of this intersection with the sphere. And then I integrate that with respect to volume on the base. Right? That's what
Right.
this
So
is.
fixing a point, we first do the integration on the fiber,
On the
then we
fiber.
come down and do the
Then
whole
you
integration.
integrate over the base. Then you integrate over. That's what this formula above is doing, right? You're integrating for each point P, you're integrating F over the fiber, and then integrating over the base. And in each case, the integral over the fiber is with respect to volume measure of the fiber, dvol TP1M, and then the integral over the base is with respect to volume measure of the base, Riemannian volume of the base. Is it clear?
Now it is clear, sir. Yeah.
Yeah, now this, so we've proved this, right? We've proved this, this one, yeah. We proved this for function with a small support in a small neighborhood where we could have a nice chart. But then for a general function, you just use a partition of unity, right? And you split it up as a sum of such functions. Is it clear? So I'm not writing that.
Yes, sir. Yes.
Yes?
A standard partition of unity argument.
Right, right. By a partition of unity. I mean, this formula holds if F has support in a small chart. And then for a general function, you can write it as a sum of functions with support in small charts by writing F as F into summation phi I. And so that's summation F phi I. And so then you just apply this formula to each F phi I. And then you add back up, right? Yes?
Yes.
Yes, sir.
Okay.
Yes.
Okay. So that's it. Okay, so once you have this formula, then this works for continuous functions. Then by passing to limits, you can get it for step functions and for indicator functions and so on, right? Indicator functions of open sets. If you apply this to an indicator function, you'll get this formula below, right? Yes.
What you asked, sir?
So I'm saying applying this formula holds for F, which is continuous with compact support, but by using dominated convergence, I can apply this to indicator functions of compact open sets, right? So
yeah, we can approximate. Yeah.
We can approximate indicator functions by continuous functions, right?
Yes, yes.
In L1 norm. So then these integrals will converge. And so if I put F equal to indicator function of U, then I get the second formula, right?
Yes, sir. Yes.
Okay, so putting f equal to indicator function of u. Okay, because the integral of f d lambda p will be just the lambda p of the intersection of u with TP1m, right? This inner integral will just be lambda p, this measure, lambda p of u intersect TP1m, right? When f is an indicator function of u. Is it
Yes,
clear?
sir. Yes.
So
Yes,
now
sir.
is it clear? So this is how one calculates the Riemannian volume measure of the unit tangent bundle. All right. So I just wanted to do this calculation for you because now you have a concrete picture of how to actually compute this Riemannian volume measure, right? Does it make sense?
Yes, sir. It is clear.
Okay, now it's clear. Yeah. Okay. Okay. All right. Okay, so we spent a lot of time, but I think it's worth it to understand, instead of some abstract measure which is given by some abstract, volume form, Riemannian volume form, we have an actual explicit, computation. In terms of Riemannian volume of the base and Riemannian volume of the fibers, right? It's like a product measure. It's like a product measure. Do you understand?
Locally, it is a product measure, basically. Yeah.
Something like that, yeah.
I mean, if I look
Something
at
like
small scales, then it will be a product.
It's like a product measure. If you take so it's a fiber bundle. So that means you have local trivializations, right?
Yes, yes.
So local trivialization will be a map to, like if I take an open subset U in the base in M, and I look at T1 of U, right? So then
Yes.
my local trivialization will map T1U to U cross Sn minus 1.
Exactly, yes.
And here it will become product measure. So
Yeah.
right? Here it will become exactly product measure.
Right. Yes.
Here.
In the fiber direction, we have it is finite volume.
Right. In the fiber direction, this is compact. It's a finite. It's just you can normalize it to be a probability measure. So
Yeah.
yeah. Okay, is this all right? Fine. Yeah, so locally it's product measure of the Riemannian volume of the base with Riemannian volume of the sphere. That's the message. That's the message. So here lambda goes to product measure. T vol M cross T vol. Okay. Okay, so let's stop this meeting since there's less than 1 minute and let's join in the next meeting. Okay.